Hello everyone. Today we are going to learn a very important chapter, dual nature of radiation and matter. In this lesson, we will understand how the light behaves both as a wave and as a particle. And also we study about how the matter shows some wave properties. Let's begin the lesson. To begin with the lesson, we must understand the electron emission. What do you mean by electron emission? So electron emission means the process by which the electrons come out from the surface of a metal. Okay. So there are three types of the electron emission. First one is the thermionic emission, second one is the field emission, and third one is the photoelectric emission. Now we will see what is thermionic emission. Okay. Thermionic emission is nothing but the electrons are emitted when the metal is heated. Okay. So when the metal is heated, the electrons will be emitted from the surface of the metal. This process is said to be thermionic emission. Okay. The next one is the field emission. What do you mean by field emission? Here, the electrons will come out from the surface of a metal due to a very strong electric field. If you apply a very strong electric field, then the electrons will come out from the surface of a metal. Okay. The third process is the photoelectric emission. What do you mean by photoelectric emission? Here, the electrons are ejected when the light falls on the metal. Okay. When the light falls on the metal, the electrons are ejected. This process is said to be the photoelectric emission. In this chapter, we will mainly focus on the photoelectric emission. In this, we will study about the Hertz observation. Okay. The first experimental evidence of the photoelectric effect was given by Hertz. Okay. He is the first person who gave the experimental evidence for the process of photoelectric effect. Okay. So now let's see now let us see what is his observation. He first noticed that when ultraviolet light fall on a metal plate, then the sparks across a detected gap is increased. This is what is first observation. Okay. From this, it is proved that the ultraviolet light is capable of releasing the charged particles from the metal. Okay. This is the observation made by the Hertz. So previously we have studied about the Hertz observation. In this we will study about the Halbert's and Lennard's observation. Okay. So here the first Halbert's observed that a negatively charged zinc plate loses its charge when the ultraviolet light falls on it. Okay. So what when ultraviolet light is fall on a negatively charged zinc plate, the zinc plate loses its charge. Okay. Then he performed a better experiment using an evacuated glass tube with two electrodes. Okay. So Leonard used a evacuated glass tube with the two electrodes. He saw that when ultraviolet light strikes the metal plate, electrons are emitted and the current starts flowing. The moment when the ultraviolet light is stopped, the current becomes zero. So this clearly confirms the photoelectric effect. As soon as the ultraviolet radiations were stopped, the current flow also stopped. Halberts observed that a negatively charged zinc plate loses its charge when it was illuminated by the ultraviolet light. Okay, so the above observations suggested that the light behaves like particles carrying energy. So this was a major shift from the classical wave theory. So now we will study the experimental study of photoelectric effect. Okay. So here the aim of this experiment is to study how the light causes the electrons to eject from the metal surface. Also, we have to study about some effects, that is, how the intensity, frequency, and the applied voltage will affect the photocurrent. Okay, we will study about these parameters in a detailed manner. First, you see the diagram. You see the diagram. In this diagram, we are having a small quartz window. Okay, so that will here the glass bulb. We can use the glass or the quartz bulb that may contain emitter and the collector. Here, the C is, that is the cathode, is nothing but a emitter, and the A is a collector, that is the anode. Okay, so what is a emitter or a cathode doing? Here, if you see the cathode, that is usually a metal plate, usually cesium, potassium, sodium, and zinc. Okay, so that will emit the electrons when light falls on it. So, what is a collector or anode here? It is nothing but a metal plate that collects the emitted electrons. Okay, so here the emitted electrons will be emitted by the C and the collected by the A. And then here we have used a evacuated glass tube. Okay, what do you mean by evacuated glass tube? That is, the tube is evacuated means all the air is removed. Okay, so what is the purpose? Is so that the electrons can move freely. The tube is usually evacuated, that is, all the air is removed so that the electrons can move freely. Okay, the next one we are having the source S. What do you mean by source S? Source S is nothing but adjustable light source. Here usually we are using a adjustable light source so that only we can vary the parameters, intensity and frequency can be so that changed so that we can vary the parameters. So usually adjustable light sources used. What are the commonly used light sources? Mercury vapor lamp, and we can use the filters to select the ultraviolet, blue, green, etc. Okay. The next to see, we are having the variable potential supply. Here we are having the battery with a rheostat or a variable voltage source is connected between the cathode and the anode. Okay. So here the voltage may be positive, voltage can be positive to attract the electrons, or the voltage may be negative to repel the electrons to measure the stopping potential. Okay. Then we are using a very sensitive ammeter to measure a very small current. Here you see the current is measured in terms of the micrometer. Micrometer means the current is in the range of 10 power minus 6. Okay. So the next we are having the commutator. You see in the diagram. In the diagram we are using the commutator. Commutator is a word you come across in the AC, right? So here also not exactly the same device what we are using in that. Here the commutator is the commutator is nothing but used to reverse the polarity of the applied voltage. Okay. The commutator switches the battery connection so that either anode becomes positive, that is attracts the electrons, photocurrent increases, or anode become negative, that is repel the electrons, photocurrent decreases and eventually becomes zero. Okay, so here the function of the why we are using the commutator is mainly to study the saturation current, stopping potential, and the effect of the potential on the photocurrent can be studied by using a commutator and reverse the polarity of the applied voltage. Here comes the first observation, that is the effect of intensity of the light on the photocurrent. So in the experiment itself we have seen by varying what are the some parameters of the light, we are going to see what is the effect of varying some parameters. Okay, the first graph is the intensity versus photoelectric current. When the intensity of the incident light increases, the photoelectric current also increases. This happens because if the light intensity more means more photons will strike the metal and hence more electrons are emitted per second. So the photoelectric current increases. Okay, so that's what it is given as a graph. When the light intensity increases, the number of photons striking the metal also increases and hence more electrons will be emitted per second. So this will increase the photoelectric current. You see the diagram? Now let us see the effect of potential on the photoelectric current. When we change the potential between the electrodes, the photoelectric current also varies. For a given intensity, let us consider, first you consider the graph for the intensity I1. For a given intensity I1, you see the graph between the collector plate potential and the photocurrent. When we increase the positive potential on the collector plate, more electrons will be collected and the current is increased. Okay, so you consider now the I1 graph. Initially, you see the current is increasing. After that, the current is saturated. Finally, it reaches a maximum value called saturation current. Here, why the current becomes saturated means in every metal has particular number of electrons. Okay, if all the electrons will be collected, then the current will become saturated. When we apply a positive potential, the photocurrent increases. After some time, the photocurrent becomes a saturated value. Okay. Now we are going to see about the stopping potential. Okay. When we apply a negative potential to the collector plate, to consider, now we are applying the negative potential to collector plate. So this is possible using the commutator. Okay. While studying the experiment of the photoelectric effect, we have used a commutator that is used to reverse the polarity of this potential. That's why we are using a commutator that is used to change the polarity of our potential. Okay. When we apply a negative potential to the collector plate, it opposes the electrons. You see, the minimum negative potential at which the photocurrent becomes zero is called stopping potential or cutoff potential. See the diagram? What is a stopping potential? The minimum negative potential, that is a minimum retarding potential at which the photocurrent becomes zero is called as stopping potential. Okay, so that's what given in the graph. You must know the definition for the stopping potential. So what is the saturation current? The maximum value of the photoelectric current is called saturating current. What is the stopping potential? The minimum negative potential. The minimum negative potential is called, that is a retarding potential. Okay, retarding potential that is given for at which the photocurrent becomes zero is called stopping potential or cutoff potential. So you have now you must know the definition for the saturation current and you must know the definition for the stopping potential. Okay, the minimum retarding potential that makes the photoelectric current zero is called stopping potential. So we have studied the photoelectrons are emitted in the photoelectric effect. What is the maximum kinetic energy? Now let us see what is the maximum kinetic energy of these emitted electrons. Okay, so we will see the kinetic energy relation. The maximum kinetic energy of the electrons is given by the formula Kmax equal to E into V naught. This is one of the very important formula. Okay, what is V naught? V naught is nothing but the stopping potential. The definition, what is the definition for the stopping potential? The minimum negative potential, the minimum negative or the retarding potential at which the photocurrent value is zero is called stopping potential. Okay, here the V naught is the stopping potential. So at this point, even the fastest electrons are unable to reach the collector. Okay, so till now we have studied when a positive potential is applied, the number of the photoelectrons emitted will increases and the photocurrent will also increase. Okay. After some particular time period, since all the electrons will be collected, the photocurrent will become a saturated value. Okay. Now we are applying the minimum negative potential at which the current becomes zero is called as a stopping potential. Okay. So now let us see another important graph that will give the relation between the intensity. This is one of the graph that provide the relationship between the stopping potential and the intensity. Okay. So now we are keeping the frequency as a constant one. Let us consider the frequency for a given frequency. Let us consider for a given frequency, the stopping potential does not depend on the intensity. That is what the conclusion of this graph. What is the inference from this graph? For a given frequency, the stopping potential does not depend on the intensity. Okay. All of you see the first one, that is for the intensity I1. What happened? You see first at the positive side. Okay. Later we see the negative side. For the I1, you just consider the positive side. In the positive side, what happened? The current increases when we increase the positive potential. Okay. After some time, it becomes saturated. Now, the intensity I2 is increased, and for that, the corresponding photocurrent is given, and for similarly for the I3. So here the I3 is greater than I2, and I2 is greater than the I1. So here you see for I1, the photocurrent is some value, and for the I2, you see the photocurrent increases, and for the I3, when we increase the intensity, the photocurrent increases. Okay, that is the first inference. When we increase for a given frequency, if we increase the intensity, then the photocurrent increases. Okay, that's what we have analyzed in the positive side. Now you come to the negative potential. So now we are applying at a intensity for a given frequency, and for the intensity I1, we are at one particular point, that is at minus V naught. Minus V naught is the retarding potential at which the photocurrent is zero. Okay. So this is called the stopping potential. Okay. Now we are increasing the intensity. See what happened? If you are increasing the intensity, now the intensity is I2. Even though we are increasing the intensity I2, see what is the stopping potential for a given value of I2? It is same. Now we are increasing the intensity I3, and for the I3 also you see the graph at the negative part, the stopping potential will be the same. So whatever be the intensity, whether it is I1 or I2 or I3, that is such that I3 is greater than I2 and I2 is greater than I1. Whatever be the value, the stopping potential value does not change. So what is the inference from this? For a given frequency, the stopping potential does not depend on the intensity. Okay. So what is the meaning for this? This means the kinetic energy of the electrons depends only on the frequency, not on how brightness the light is. Okay, because the intensity is a parameter that is related with the brightness. Okay, this is the indirect information we got from this graph. Okay, it's a very important analysis. That is, the kinetic energy of the electron depends only on the frequency and not on the how bright the light is. That is, does not depend on the intensity. Now let us study the effect of frequency on the stopping potential. That is the effect of the frequency of the incident radiant on the stopping potential. Okay, you see the graph. You see, for the frequency u1, the stopping potential is minus V01. Okay. For the frequency mu2, the stopping potential is minus V02. For the frequency V3, it is minus V03. You see, as the value of the frequency increases, the stopping potential also increases. Okay. In the previous graph we have studied, when we increase the intensity, whatever be the intensity, that is when we increase the intensity from I1 to I2 and then from I2 to I3, such that I3 is greater than I2 and I2 is greater than I1. Whatever be the value of the intensity, the stopping potential the same for the given frequency. That's what we have seen in the last graph. Now you consider this one. Here, when the frequency increases, the stopping potential also increases. It is not constant. So the stopping potential is, the conclusion is, the stopping potential is independent of the intensity for a given frequency. Okay. But the stopping potential is dependent on the frequency. If the frequency increases, the stopping potential also increases. What is the inference from this? This means the higher frequency photons will give high energy to the electrons. Now we see another important factor, threshold frequency. Okay. Each and every metal is having certain threshold frequency value. Only if the frequency of the incident radiation is above this threshold frequency, then only the photoelectron emission will take place. Okay. Now you consider the metal A. For the metal A, the threshold frequency is given as nu naught, and for the metal B, the threshold frequency is given as nu naught dash. Okay. You see the condition. Till the nu naught, is there any photocurrent? So till the nu naught, there is a no photoelectric emission. When the frequency of the incident radiation is greater than the nu naught, then only the photoelectric emission will take place. Okay. Similarly, for the metal B, you consider the threshold frequency is nu naught dash. If the frequency of the incident radiation, when the frequency of till V naught nu naught dash, till the threshold frequency, the photocurrent is 0. Only when the frequency of the incident radiation is above the threshold frequency, there is a photoelectric emission. Okay. So, what is the definition for the threshold frequency? There exists a minimum frequency below which no photoelectric emission occurs is called threshold frequency. Light below this frequency fails to emit electron no matter whatever be the intensity. Okay. So, this explains the limitation of the wave theory or wave theory failure. Okay. So, according to the classical wave theory, if you consider the classical wave theory, the energy depends on the intensity. Okay. And then the electron emission should occur after some time delay. According to the classical wave theory, the energy depends on the intensity and the emission should occur after some time delay. Okay. But here the experiments showed immediate emission and dependence on the frequency. Thus, the wave theory failed to explain the concept of photoelectric effect. Okay. So, according to the classical wave theory, it has certain limitations on the photoelectric emission. Okay, so now Einstein solved the problem by proposing that the light consists of the packets of energy called photons. Okay, so each photon, the energy associated with each photon is h into nu, and is the frequency. He also gave the Fermat's equation: kinetic energy is equal to h nu minus phi naught. This is said to be the work function of the metal. Okay. So the above equation gives the condition for the photoelectric emission. Listen, most of the students will get confused with the stopping potential and the work function. Okay. So the first we have seen the formula, the maximum kinetic energy kV max is equal to E into V naught, where V naught is the stopping potential, that is the minimum negative retarding potential at which the photocurrent is zero is said to be the stopping potential. Okay. Now the Einstein equation is E V naught is equal to h mu minus phi naught. Here this phi naught is said to be the work function of the metal. So from this we can calculate, from this formula we can calculate what is the stopping potential, V naught. Okay. So here V naught is equal to h mu minus phi naught by E. That's what it is given. Surely problems will be asked on this part. So don't get confused with the work function and the stopping potential. The definition for the work function is the minimum energy required to remove an electron from the surface of the metal is called work function. It is the least amount of the energy needed to free an electron that is bound to the metal. So now we'll see the particle nature of the light. According to the photon theory, the light behaves like a particles called photons. Okay, each photon has an energy h nu and a momentum h nu by c. All the photons have the same frequency, have the equal energy. That is one of the important consideration of this theory. That is, all the photons of the same frequency will have the equal energy. Okay. Then photons are electrically neutral. Photons are electrically neutral. Energy and momentum are conserved in photon interactions. Photons are electrically neutral and so they are not deflected by electric and magnetic fields. Okay, it is one of the important MCQ that is frequently asked in the board exams. Photons are electrically neutral and that's why they are not deflected by the electric and the magnetic fields. Okay, and another one more point is in a photon particle collision, the total energy and the total momentum are conserved. Okay, however, the number of photons may not be conserved in a collision. Okay, it is also one of the very important point. Total energy and the total momentum is conserved, whereas the number of photons may not be conserved in a collision. Now we discuss about the wave nature of the matter. Okay. So de Broglie proposed that matter also behaves like the waves. Okay. So the de Broglie proposed that the wavelength associated with the particle of the momentum is given as lambda is equal to h by p. So this is called de Broglie wavelength. The de Broglie wavelength is given by the formula h by p. You know very well the formula for the p is equal to momentum is nothing but mass into velocity. So the formula can be written as h by m into v. Okay. So the lambda is said to be the de Broglie wavelength. Formula is h by p where p is equal to m into v. This is known as de Broglie relation and this wavelength is known as de Broglie wavelength. So, according to the de Broglie, he proposed that Matter also behaves like a waves. So he gives the relation lambda is equal to h by p, that is equal to h by mv. So the electrons, protons and even large objects have wave-like nature. Now let us see the wavelength of the electron. The kinetic energy formula for the kinetic energy is half mv squared. That is nothing but p squared by 2m, where p is equal to m into v. Okay, so using that relation, if you find out the lambda, that is h by p, if you substitute the value, then you will get the lambda is equal to h by square root of 2 into m into e into v. Okay, so what is the meaning for this is when an electron is accelerated through a potential V, then its de Broglie wavelength is calculated using the formula lambda is equal to h by square root of 2 into m into e into v. So while substituting the values, we will get lambda is equal to 1.227 by square root of v nanometer. Heisenberg stated that we cannot simultaneously measure the position and momentum of a particle exactly. The more accurately we know one, the less accurately we know the other. So before moving to this experiment, you must know about the diffraction. What is a diffraction? Diffraction is the bending or spreading of the waves when they pass through a small opening or around the edges of an obstacle. Okay. When a wave encounters a narrow slit, a sharp edge, or an obstacle, it does not travel in a straight line. Instead, it spreads out into the region behind the obstacle. This spreading is called diffraction. For example, sound bending around a wall, water waves spreading after passing through a gap, light waves showing fringes when passing through a small slit. So this diffraction will prove you the light behaves as a wave. Electron also behaves as a waves, that is matter waves. Now we will see the experiment in a detailed manner. De Broglie predicted that the matter behaves like waves and has a wavelength lambda is equal to h by p, that is equal to h by mv. Okay, but this needed the experimental proof. Davison and Germer provided this proof by showing that the electrons form a diffraction pattern, just like X-rays or the light rays. Okay, here you see in the apparatus, it's a very simple experiment only. Here we are having the electron gun. This electron gun will emit a beam of electrons, and here the electrons are produced by the thermionic emission. Okay, and the electrons are accelerated by you know very well, the electrons are accelerated by the potential V. So this nickel crystal has regularly spaced atoms like a crystal lattice, and it acts as a diffraction grating for the electrons. Okay, here the nickel will act as a diffraction grating for the electrons. We have studied no in the Young's double slit experiment. Rotatable detector. Here the rotatable detector detects the intensity of the scattered electron. Rotatable detector we are having, so that will detects the intensity of the scattered electrons and can be rotated to measure the intensity at different angles. Okay. Vacuum chamber, it contains the electron gun, crystal and the detector. This vacuum chamber contains electron gun, crystal and the detector. Prevents electrons from colliding with the air molecules. So here what is explained in this experiment is the electrons are emitted from the heated filament. Okay. They are accelerated through the accelerating voltage V. These electrons will strike the nickel crystal. They get scattered in the different direction due to the irregular arrangement of the atoms. A movable detector measures the intensity of the scattered electron at various angles. Now we will see some of the observations of this experiment. When the accelerating voltage was 54 volts, something special happened. The detector recorded a strong peak in the scattered electron intensity at an angle of 50 degrees. This peak is similar to the maxima seen in the X-ray diffraction pattern. This clearly indicated electrons undergo diffraction, which is a property of a wave. The de Broglie wavelength associated with the electrons for the accelerating voltage 54 volts is given by lambda is equal to h by p is equal to 1.227 by square root of v nanometer. So the lambda is equal to, if you substitute the v value is equal to 54, then you will get the value as 0.167 nanometer. Thus, there is an excellent agreement between the theoretical value and experimentally obtained value of the de Broglie wavelength. Davison-Germer experiment thus strikingly confirms the wave nature of the electrons and the de Broglie relation. So, in this chapter, we learned light behaves both as a wave and particle. The electrons show the wave nature. Photoelectric effect supports particle nature. Davison-Germer experiment confirms the wave nature. Thus, radiation and matter both have dual nature. Thank you.